I hope you all are safe and staying at your home. So, we all know that artificial intelligence, that is AI, deep learning, and neural networks, represent incredibly exciting and powerful machine learning based techniques used to solve many real problems. And AI and basically artificial neural networks have the ability to learn and model non-linear and complex relationships, which is really important because in real life many of the relationship between inputs and outputs are non-linear as well as complex. Understanding artificial neural network with regression. Before going on to that, let's first understand what is ANN or artificial neural network. ANN usually simply called as neural networks, that is NNs, are computing systems vaguely inspired by the biological neural networks that constitute animal brains. And ANN is based on collection of connected units or nodes called artificial neurons, which loosely model the neuron into biological brain. ANN is probably the first stop for anyone who enters into the field of deep learning. Inspired by the structure of natural neural networks present in our body, ANN mimics a similar structure and learning mechanism. ANN is just an algorithm to build an effective predictive model because the algorithm and so its implementation resembles a typical neural network. The functionality of ANN can be explained in five simple steps. So first is read the input data. Second, produce the predictive model with mathematical functions. Third, measure the error in predictive model. Fourth, inform and implement necessary corrections to the model repeatedly until a model with least error is found. And last but not the least, use this model for predicting the unknown. Now coming on to the architecture, you can see it as the input layer in yellow circles, it is the neuron hidden layers, and these are the output layers. So these are the input layers which receives input. So basically it is a set of nodes which take the input data as one per node. For a regression problem, if we are having 10 columns per feature, then we need to set exactly 10 nodes in the input layer. Now comes the hidden layer. So an ANN can have one or more hidden layers. As you can see here, there are two hidden layers and each layer can have number of neurons. So basically these are the neurons and it can have number of neurons, it depends on you. And each neuron is a combination of a computational unit and an activation unit. So this is the computation unit and an activation. This is the combination of both of them. Now comes third, the output layer. So each ANN has one output layer which provides the output of the model. If the model is regression, then the output layer will have only one node. So you can see here only there is one node. The output of this model is the y predicted value given in the input layer. Okay. So if the target variable is categorical data of two classes, then the output layer should have two nodes and the activation function should be sigmoid. If it is a multi-class classification, then the output should have the node exactly the same number of classes, the target variables, and the activation function should be softmax at that point of time. So here if it is not that case, then you can use sigmoid. If the activation function is sigmoid or softmax, we will get the probability value For all the nodes in the output layer, the index of the highest probability value is the output. So you can see here, this is the probability value. So here it is 0.3 and here it is 0.9. So the probability value whose value is highest will be our output. The another one is weights and bias. So each connection mentioned in this figure is assigned with weights and bias. Okay. So the weight value is initially assigned randomly and will be updated by the optimizers in each epochs. So as you will run the epoch, the optimizer will update the weights automatically. And the bias value is used to avoid the weights to become zero. Basically, we don't want that the weight should become zero, so we use bias value for that. Now implementing ANN for linear regression. So basically we have to understood that each of the neuron in the ANN except the input layer produces an output. So basically you can see here that these are the things that is not producing any output, but if you see that hidden layers are there or the final output, they all produce some sort of outputs. Alright, so the output is based on the function that we use. The function is generally referred as activation function, and ANN is mainly used for classification purpose. Generally, sigmoid function or other similar classification algorithms are used as activation functions. But as we are now trying to solve linear regression problems, our activation function here is nothing but a simple linear equation in the form, as you can see here. This is the form in which the equation is there. So y equals to w0 plus w1 x1 plus w2 x2, so on up to wn xn, where x1, x2, x3, these are the independent attributes in the input data, and this w1, w2, wn are the weights, or you can say the coefficients to the corresponding attributes, and w0 is the bias. Because our output should be a single linear line, we should configure our ANN with just one neuron, as the output of this one neuron itself is a linear line. This neuron will be placed in the output layer, and the hidden layers are required when we try to solve linear regression problems. Consist of an input layer with all the input attributes and an output layer with just one neuron. Now we have finalized the structure of our ANN. Now our next task is to actually write code to implement it. So we'll be implementing this simple ANN from scratch, as that will help us to understand a lot of concepts in already available ANN libraries. This process involves feeding inputs to a neuron in the next layers to produce an output using activation functions, and this process is called a feed forward. And after producing output, error or loss is calculated and correction is sent back to the network. Basically, if there is any error or something, so this will send it back to the network, and this process is basically called as a back propagation. We'll also use some standard terminologies for our ANN network, such as network topology, etc., which we'll see in the upcoming code. So let us understand with the help of this code. So here basically we have imported all the necessary libraries. Now we'll be providing input to the code such as 3, 2, 1 basically. So you can see here we are providing this input from here, and here the total number of values present in the list indicates number of layers that we want to configure, and each number in the list indicates the number of neurons inside each layer. So basically this structure can be called as a network topology. However, as we are like solving regression problem, we just need one neuron as the output layer. So we will just pass the input list as 1. And in our approach to build linear regression neural network, we will be using stochastic gradient descent, or SGD in short, as an algorithm, because this is the algorithm which is like mostly used even for like classification problems with deep neural networks, which means multiple layers and multiple neurons. So now let us create a class called network. So here we have written a class network and initialize all the required variable in the instructor. So basically here I have defined all the necessary layers that in it I have initialized all the things, that the layer, bias, topology and outputs and weights. A self.output holds the output of each neuron. It will be initialized accordingly with sufficient sized list based on our output. Due to this, we have like taken it as a variable, so it can vary. In the fit function, we know that the gradient descent algorithm requires a learning rate, or ETA in short. We have defined learning rate as ETA, and number of iterations as epochs. So we will be passing all these values in a list to the program along with the training data. Basically you can see here, this is the feed forward and back propagation. So basically this functions is just forming a simple linear equation y equals to mx plus c. In SGD algorithm, we continuously update the initialized weight in the negative direction of the scope to each minimal point. As you can see here, this is the error function. So basically we will calculate the errors and with the function that E of W equals to sigma W0 plus 1 W1 x1 minus y1 whole square plus W0 plus W1 x2 minus y2 square, and so on. So here I have not taken 1 by 2 as a scaling factor to the equation. You can take like if desired. And also in SGD, only one row is passed to the error function every time to calculate the error, and hence like if we differentiate this equation with respect to each of the weights, that is W0, W1, W2 and like so on, we get the equation like deba E0 equals to 1, deba E1 equals 2 into W0 plus W1 x1 minus y1 into this will also need to like basically it is deba E1 by deba W1. So basically you need to differentiate all square, so it will be 2 into this, and you need to differentiate this bracket also again. So we will get this equation, and after calculating the slope with respect to each of the weights, the weight will be updating to the new value in the negative direction of the slope with the equation like you can see here. This is the equation that will be updating the value. So now all this logic in the back propagation, it is implemented. So basically we implemented all this thing in this back propagation, all the equations that I have explained you earlier. So all this thing has been implemented here, and the weights like all the SGD one is implemented over here. Okay, so in order to like visualize the error at each step, we wrote a function called mean square error here, the get MSE, and a square error for each. So we'll calculate the error from this function, and the mean square error for the full data set will calculate it from this function, which will be like calculated for each step in an epoch. And having this model built, we define a method which takes some input and predicts the output. It will like take some input and predicts the output at the each step. So that's it. We have built a simple neural network for linear regression model, and also predict the value for unknowns. It will also plot and shows how the error is getting reduced in each steps. So if we run this code, we'll get this as the output, and the plot will be like this as shown here, that how the error is like decreasing, and here the error decreasing rate is minimal, like almost constant. So these are some of the references that I have taken for my use. So the code is taken from this last link. So thank you everyone. I hope you like my video. Do like, share and subscribe to my channel. And stay safe, stay at home.